Okay, we're going to start off our sixth presentation with Bruno Ribeiro, and his topic is blazing fast chemical sensing.
Hi, my name is Bruno Ribeiro. Ashraf Alam is supposed to come anytime soon. So here, here I have a temperature sensor. If you put in your ear, 3 seconds later, you know your temperature. But if you think about chemical sensing, putting in your skin, that will take hours to give you a reading. So what we want to achieve here is blazing fast chemical sensing. And more specifically, we want to define the data science foundation for this. So we have, in physics-based modeling, we have models that don't need a lot of data, and they always give you sensible answers. However, if you put the sensor, a chemical sensor in the field, it becomes this little monster here that doesn't quite fit the physics. So you have a number of modeling assumptions that you need to make, and once it's formulated, the functional form, it cannot evolve online. So the advantage is, on the other hand, machine learning has been very successful exactly because it has the opposite of physics-based modeling. It's very flexible, and it can predict very complex phenomena. However, it needs a lot of data to be safe in critical applications. And it's a shaky foundation because if you give an example, an environment that hasn't seen the training data, who knows what kind of answer it will give. And the time to get these answers correctly is now, because if you try to mix physics with machine learning, then if you do a poor job, that will be on the news the next day, and that will put everybody backwards a few years, right? So we really need a new foundation for this, and something that is very solid. And our choice of chemical sensing is because, first, it has a number of applications in healthcare. Once you have fast chemical sensing, you'll be able to unleash a lot of applications in healthcare monitoring, precision agriculture, and homeland security, and et cetera. And this is a very high risk, high payoff proposition. Physics-based machine learning is just in its infancy. The first workshop was held December last year. And specifically, the physics-based models for chemicals is also in its infancy. We don't yet know how to do this specifically for fast sensing. So what we want here is to create a hybrid model that mitigates the drawbacks of each proposition. And specifically, the main insight for us is that we want to teach neural networks physics, so that if they see no data, they can give you an answer that is sensible. And with data, it's able to adapt the physics to the data. And that will build on the complementary strengths of deep learning, which is being flexible, and physics, which always gives sensible answers with not a lot of data. And the symbiotic relationship that Professor Alam and I have is that I work on complex data-driven models, and he works on complex physics-based biochemical models. Technically, the time is really now, because I could not give this talk a year ago. Now we understand a lot better how to use neurogenerative models to divide the task between physics and machine learning. Moreover, we know a lot more about uncertainty quantification in deep neural networks. I'll give you, for instance, this simple toy example. So here we have responses from the sensors in this two-dimensional box. And the physics tells us that this area of chemical concentration is safe, this area is dangerous. So from the physics model, we create a number of examples to teach the neural network how to identify safe and unsafe chemical levels. And this is, without any data, the neural network at least knows which regions are which. Now, if we have lab experiments will not cover the entire space or range of environments, right? They are very expensive. So we have just a few environments where you can see that what we would see in the physics model, for instance, in this toy example, is that it's a little different than what the physics model predicts. This is the real data. And now the deep neural network, looking at the real data, updates its physics understanding to incorporate the real data into the physics. So now it gives predictions that are data-driven, but also safe regarding the physics of it. And the other important aspect, why it's now, because physics, transient modeling of these chemical sensors is just also in infancy. We don't really understand if physics is able to do fast chemical sensing. So that's one of the aspects that excites us in this enterprise that we are describing. Again, our goal is fast chemical sensing, but it's not just limited to fast chemical sensing. Once you have this data science foundation, you can think of it, there are a lot of engineering applications that need data adaptive solutions. And physics is a very solid foundation, like a steel beam, but it's not very malleable, right? On the other hand, a deep neural network is very malleable. It can make any shape. It can basically predict anything. It's like concrete without steel, but it's not a very solid foundation. You don't build houses out of concrete without anything inside. So what we are proposing here is similar, a parallel to reinforced concrete. We want to put physics inside the concrete so we can build new things. If you ever been to Barcelona, Gaudi's magnificent church, you think that you entered in a spaceship. It's amazing what can be done with reinforced concrete. None of these techniques would be able to do that. So what we want to build is physics-reinforced deep neural networks to unleash novel, dependable, flexible models where we are going to unlock a new wave of engineering applications with them. And the competition here really is just started with us, and specifically, they are focused on simpler physics, like temperature. Temperature is something we can do in 3 seconds. Or Newtonian physics. Or they are looking at applying off-the-shelf machine learning to complex chaotic systems. These are not solutions for the type of problems that we want to deal with. So why is Purdue set to lead? Professor Alam and I work on very complex modeling systems. Moreover, Purdue has industrial strength. We have amazing faculty at leading edge of printed chemical sensors. And with these sensors, we are able to, with this faculty and the amazing students that they have, they can help us get from the theory. So once we develop the theory to test fields, to industrial partnerships can be very quick. So for our benchmarks here, because now is the time, really we can't wait for NSF funding or other type of funding. We need to do this now. And it's important to point out that I will just point out this part here, the chemical estimates. So the chemical estimates, when I talk to the folks, they tell me that build this sensor, they tell me it's not possible. You can't do this in less than 30 minutes. But the question here is, it's not possible because they are thinking of doing that with steel. What if we can give them reinforced concrete? Is that something that will be possible now? And that's exactly the type of work that we want to do. Thank you.
I got a quick question for you, Bruno, about the competition that you described.
Yeah.
Okay. I mean, it is my impression that there are groups out there, I don't know about chemical sensing, but for example, in material science,
Right.
who are starting to think about and starting to apply machine learning algorithms together with physics-based models to improve materials discovery, for example, going beyond traditional, first principles, a multi-scale physics-based to bring, machine learning and deep learning. So it seems to me that there's a lot of competition out there, a lot of groups trying to bring these two modalities of simulation together.
Right, yeah,
But you don't talk about those.
Right, so here we listed the ones that we think are the closest because they are talking about sensing.
I see.
But I would say this, these folks are doing a more traditional, they are piggybacking physics to deep learning. So deep learning here, physics here, or physics here, deep learning here. We are not talking about putting them like this. We are talking about merging them.
Okay.
So we are talking about reinforced steel. So we want to put physics inside deep learning, not together.
Okay. And very quickly, the material genome project, where the machine learning is used, it is all in other related work. They are trying to sort of interpolate in terms of numerous functions. These are kinetic systems, which are evolving as a function of time. So that brings in an additional degree of complexity. And these are all in wild. So sensors are in the wild, so not in a controlled lab condition. That makes this problem particularly interesting and difficult.
I had a question. Isn't sort of one facet of the competition here just people doing multi-scale physics models, right? So you combine physics with other kinds of physics? You don't have to answer. Tomas already answered.
Yeah, so one of the interesting aspects I think that to emphasize is that in deep learning specifically, you can build really complex models from the data. So we adapt from the data. You're not setting up, you're not thinking at home how the physics would happen, and you wake up in the morning and you build a model. From the data, automatically it adapts to the situation. So you can think of a data-driven adaptive model, but that needs a lot of data. So we are trying to solve that by infusing physics inside the deep learning model. So we think it's quite different.
But the multi-scale models are either time-consuming, or if you want to simplify it, then it relies on assumption. And here, when you put the sensors out in the field, the environment is not controlled. And so therefore, you cannot a priori develop any model, multi-scale or otherwise. You have to have a model, but then supplement it with the data, what is the data is trying to tell you, and then combine them. Over time, of course, once you know what the exact conditions are, one may be able to evolve a multi-scale model. But right now, the assumptions are not even clear. So therefore, you cannot develop any multi-scale model.
Even if model discovery from the data first.
Exactly, exactly. That is because this sensor is not in the lab, but in the wild. So therefore, you have to develop model based on the data.
What do you sense?
In this particular case, it is nitrate sensing in the soil. But you could see the generality of the problem, because this is sort of in any sensing data that you have could then be adapted to this.
Thanks. I get the analogy of having the steel inside the concrete, but I'm wanting to know what practically that really means for combining physics with the machine learning.
Oh.
So it sounds to me like, so just tell me if you're saying it's not one over the other, so you're talking about sequencing, so is it, you're saying that you'll use these simultaneously in some way? I'm wondering what you mean. Do you start with the physics model and then do it?
You start with the physics model.
Iteratively? And is what's different about your approach that you go back to the physics model and then change it and then do it more iteratively and then go back? That's what's distinctive?
Yeah, so the approach it has three parts. One is we use the physics model to teach the deep learning how to react to new situations. So it's a deep learning centric approach in that sense, that the physics model is being mimicked by the deep learning, but we never really get rid of the physics model. So whenever we are actually making predictions on the field, and the neural network says, oh, this part I don't know, haven't seen data like this, it doesn't fit my physics, I need to go back to the physics model and ask it what the answer would be. And then it goes back. So it's really an interconnected approach.
So you mentioned chemical sensing as a major driver for this work.
Mm-hmm.
Could you speak to the potential broader applications of this, of combining, physics-based model development, and whether this is likely to be a completely different area if you expand it further, or you think this might be portable?
In terms of application, you can easily envision, for example, I work on solar cells. And over there, you have very similar problem. These things are out there, rain and shine. It's not inside the lab in a controlled environment. It produces a time sequence of data, and you have a problem of predicting something down the road. Based on a lot of data, you have to sort of discover the degradation modes that are relevant, and thereby predict how it's going to behave 30 years down the road. So therefore, this whole class of problems where you measure to predict something down the road over a broad range of environmental conditions, that would fall into this category. And this class of problems have never been attacked, in a successful way. So the hope is that it will be able to do so here.
I also picked up on the fact that that you potentially, at least with this lead application, you have a evolving system. So time is an issue, and it doesn't make any difference how long you go. You will never have the perfect model because it keeps changing. So that's also part of the innovative aspect?
Yeah, so one other aspect that Ashraf and I talk a lot is sensors degrade over time. So whatever you build now, the model that you build now will not be used for in a day or two. But the data is telling you that, right? So as you observe more and more data, you can adapt, the data can tell you how to adapt your physics to the evolving conditions now. So I think this approach has the advantage of the flexibility of machine learning that can adapt.
Thank you very much.